Hey everybody, and welcome back to CSE 1322. This is the beginning of module number 8. In this module, we're going to talk about data structures. So basically, thus far in 1322, you've been looking at things like arrays and array lists, and that's really all that you've had. But we're going to look at some other data structures. Each of these data structures has the ability to do something that the other ones don't. So a good thing about arrays is that they occupy a set of space in memory, and they're very easy to put an item into or out of any particular cell. You can put something into cell 3 and take it out of cell 3, and both of those are very easy operations to do. But there are some things that arrays are not very well suited for. For example, if you need to be able to put new items in at the beginning of the array, then you've got to move everything down in the array every time that you do that. Whereas if you put things in at the end of the array, then you don't have to do that. But sometimes it's useful to be able to put things in at the beginning of the array, and we're going to see examples of that as we go. So this is going to be a module that's going to be broken up into 4 different sections. We're going to do module number 1 in this video. Part number 1 in this video. We'll do part 2, part 3, and part 4 in separate videos, and we'll look at different data structures in each one of them. So let's go ahead and get started. So the first thing we're going to talk about this week is linked lists. So the idea of a linked list is, instead of having a data structure which is a fixed size, it would be nice to have a data structure that can grow and shrink as you need it. And that's exactly what a linked list does. It allows you to add one node into the list, and the list becomes one node larger. If you take one node out, the list becomes one node smaller. It automatically grows and shrinks as it is needed to. So it's very efficient on the amount of memory that it uses. And so linked lists are a really useful way to look at things. So before we take a look at the details of how a linked list is built, I'm just going to give you a visual representation of what they look like. So effectively, what you're going to have with a linked list is you're going to have some kind of starting arrow that's going to be called the front of the list, or maybe the head of the list. So we'll call it front, but it's very often called head. And what it's going to link to is it's going to link to a node that then is going to link to another node. And this is where the name linked list comes from. Effectively, each of these links points you to a node. And then the node has whatever data it has in it. So perhaps this could be a student record. And so it might have, your KSU ID and some other information like your name, your GPA, your major, all of those things could be listed inside of this node. And so the node could have lots and lots of stuff in it. And likewise, each node in the list will have the same amount of stuff in it. It'll have the ability to store all that same stuff in there. So this is the idea of a linked list. If I need to add a new node into the list, then usually the simplest way to do it would be to simply update this thing at the end to point to my new node. So I add my new node, I put my data into it, and then the link at the very end is going to no longer be linked to anything else. And the way that we indicate that is with those 2 lines. It just means that's the end of the list. So visually, this is the idea of a linked list. Java has this class built in for you, and it's literally just called linked list. So in actuality, when you want to use a linked list, all you have to do is instantiate a linked list inside of Java, and it works just like an array list. So you would import Java util linked list, and then you would create your linked list with linked list, the angle brackets which specify the type of the linked list you want to create. You give it a variable name, which in this case I called it my list, equals new linked list, and the type of the information again. Much like with array lists, what goes in these curly or these angle brackets is an object. So you can't put int or double or float in there. You have to use the object wrapper. So it's going to be integer with a capital I, or float with a capital F, or double with a capital D, or Boolean with a capital B, and so on and so forth. But if you're using a class like a dog or a student or a person or an employee or whatever else, if you've created a class, then you can certainly just make a linked list of that class. And that would be the more common scenario, is that you want a linked list of students, or a linked list of employees, or a linked list of items in your bag that you're carrying in the game. All right, so how do you add something into the linked list? Well, we're going to use the add first and add last methods. So the difference between add first and add last is which side of the linked list do we want to add the new item to? If we're adding the item to this side of the linked list here, then we would use add first. If we want to add the item to the end of the linked list down here, then we would use add last. So it's just a matter of which side do you want to use. And sometimes it's useful to put them at the front, sometimes it's useful to put them at the back. And we'll see examples of why that might matter down the road. If you want to retrieve something from the list, then you would say mylist.get first or mylist.get last. And again, that's going to give you the one from the front of the list or the one from the end of the list, depending on what you want. And you can also retrieve something from the middle, much like in an array, by saying mylist.get3. And that's going to return the fourth element because, like everything else, it's indexed from 0. So 0, 1, 2, 3 gives you the fourth element out of the list. Okay, so why does this exist if we already have an array list? It seems like the two of these things are very, very similar. So they do have a number of attributes that are the same. They are both generic, and generic means that you've got those angle brackets that you can put the type in when you create the linked list. So you can specify what type of linked list you want or what type of array list you want, because of course you might sometimes want to store numbers, you might sometimes want to store students, you might sometimes want to store dogs. The second thing that makes them similar is that they both dynamically grow and shrink. And so it might seem, well, then isn't it redundant? Like, why do we have both of these? Well, it comes down to how they're actually implemented. And so we're going to talk through the implementation for just a moment here. So we'll start off with an array list. So let me just erase this and let's talk about how an array list is implemented. So when you have an array list, the name might suggest to you that it's based on an array, and that is actually the case. Array lists are made up of an array. And if you remember in memory, if you were thinking of an array, you pretty much draw it like this. And so each cell has a number, and you put items into it. So when you make this array, maybe you made an array of characters, or you made an array of dogs, or an array of employees, or whatever it is, that's fine. Each one of those goes into one cell in here. The implementation detail of this is when you create this array at the very beginning, Java allocates all of the memory for it the moment you create it. So when you say int square brackets my array equals new int square brackets 3, at this moment in time, it creates an array that is large enough to hold three integers. So in that case, it wouldn't be like this because that's not there, nor is that. So it would look something like this, 0, 1, and 2. And so the amount of memory that uses at the moment that this statement executes is going to be 3 times the size of an integer. And an integer is generally 32 bits on most processors these days. And so 3 times 32 means it allocates 96 bits of memory in order to be able to hold your array that can take in 3 integers. And you probably think, okay, why do I care? And the answer is for 96 bits, you totally don't care. Your computer has somewhere around 8 gigs of RAM or 16 gigs of RAM. That's 16 billion bits of RAM. So allocating 96 of them is absolutely irrelevant. If you end up being a developer where you're working on things like embedded systems, then the amount of RAM is going to be much more restrictive. If you're dealing on a desktop computer or a server, today most computers are bought with large amounts of RAM because RAM is relatively cheap. But if you have something that's an embedded device, and your phone is an example of an embedded device, usually your phone will only have 8 gigs of RAM, or maybe it has 16, but probably not much more than that, unless you've got some kind of really fancy one. In general, you're more restricted in how much memory you have. And the more restricted you are, the more important it is that the people writing the software are being careful about how they use that memory. Things like a flight control system in an aircraft or a control system that's running your microwave tend to come with very small amounts of memory. And that's because it's a specifically designed system for that application, and they know how much RAM they're really going to need. And so the software has to be written with very careful attention to the detail of how much memory you're going to use. All right. So for you going out as a first time software developer, the chances are you don't really have to deal with memory management too much. You should be aware of how much memory you're using because, of course, the more your application uses, the more demanding you are from the hardware that you have to run your application. And so you've seen that sometimes you buy a game and it doesn't really work on every computer. You have to have a particular amount of memory, you have to have a particular graphics card in order to be able to run that. That's a decision that the developers made at the time that they created the game, that this was going to be the minimum requirements for that game. And likewise for every application that you build. If something is a very small application, like you build a little note keeping application, it's widely expected that it should be able to run on any phone because you shouldn't be using that much memory. You're just keeping track of a few notes. And so you would be it would be awkward if you made an application that required 8 gigs of RAM in order to do that because you were being sloppy and you weren't paying attention to how much RAM you were using. You were just allocating arrays that were way too big that you never needed. So it is important to be aware of the amount of memory that you're using, but on a day to day basis, the exact number usually doesn't matter for most applications, again, unless you're in embedded systems and whatnot. Okay, but having said all of that, when you create your array, it's important to realize that the moment that you create the array with that statement, that memory is allocated, and your application is going to hold on to that memory until that application is done or that memory is freed. And usually it would be freed by the garbage collector if you've stopped using it and it's no longer referenced anywhere in your code. But for the most part, if you allocate a memory at the beginning of your code is going to occupy that memory for the entire time that it's running, unless you go out of your way to free it up. So, if I need you to be able to store student information, and let's say a student is defined as um, I'm going to keep track of the KSU ID. I'm going to keep track of their name. I need their address. I need their phone number. I need their major. And I need a list of all the classes that they've taken, including the grade that they earned if it's a class they've already completed. Okay, so a KSU ID is about 9 digits. So that's something that could probably be stored in an integer. At worst case scenario, maybe a long, so 32 or 64 bits. That's not so bad. How big should we make the thing that's going to store the name? Well, generally, if you store it as a string, it allocates however much size it is. And so if it's a name that has 15 characters, you get 15 character size string. So you don't really have to think about that because that's one of the attributes of strings is that they just are however big they need to be. Likewise, the address is going to be pretty much the same way. You're going to have however much space you have, and the phone number is going to be 10 digits, or maybe if you're international, it might be a little bit longer, but 15 digits probably going to take care of it. But how about this one? How about all the classes that they've taken, including their grades? How are we going to store that? Well, your first instinct might be an array or an array list. So you might say, well, okay, we're going to have an array, and each cell of the array is going to list the name of the class, the professor, the time that it met, and the grade earned. And the same thing for the next class, and the same thing for the next class, and so on. So the question that I'm going to ask you is, well, how big should that array be? What's the most classes that a student could ever take? Well, at first it seems like, well, you're not going to take more than 5 in a semester. So maybe it's 5 times 2 semesters a year. That's 10 times 4 years, 40? 40 cells? Is that going to cover it? Well, what happens if you do a master's or you're doing a dual owl or something like that, a double owl? Then it could be bigger than that. Maybe it's 5 years or 6 years. What happens if you start school and then you leave for a few years and you come back and then you change major and you start another major and then you leave for a few years and you come back and you start another major? So the question is, how big should this array be when I make the array? And the answer is, I don't know. What's the most number of classes a student has ever taken at KSU? I've actually no idea, but I'm guessing it's probably hundreds, because there's probably somebody who did change majors enough times that they just kept having to take more and more classes. So how big should I allocate it? I don't want to make it so big that I'm using up memory that I don't need, but I do need it to be big enough that it's going to store every student at KSU or at every school that uses my software. So I probably need to just pick a number that's big enough that I don't think it's ever going to be a problem. So I'm going to say 500. I'm going to say there's an arbitrary number, and that number is 500, and no one should ever take more than 500 classes. What do you think is going to happen? My software is going to become very successful, and it's going to become the standard software that everybody uses for storing students. And 2 years from now, it's going to be used at a school where they don't have semesters, they have 3 week long courses. And a degree is made up of 550 courses. And then all of a sudden, my array doesn't work because I made this arbitrary number that it was going to be 500 because as best as I could tell, that was as most as anyone would ever need. So picking an arbitrary number is problematic. And the issue with arrays is that's the only way they work. When I create an array, I have to tell it upfront how big it's going to be, and that's how big it is forever. And if I'm wrong, my application just doesn't work anymore. Once a student comes along who needs 501 classes, they no longer work in my application, and I'm going to either have a bug where the 501st class just disappears. That's not great. You spent all that time and money passing a class, and my software doesn't know how to handle it. Or that's the best case scenario. The worst case scenario is this is going to produce a security vulnerability. Because when they go to write the 501st class, where does it actually store it? Well, maybe it stores it in a place that it's not supposed to store it because the array isn't big enough. So, this is how security vulnerabilities happen. This is how bugs happen in software, where there's an artificial limit that seems like it's the right number, and then it turns out to not be right. And you might say, okay, well, this is a made up example. Who cares how many classes people take at KSU? Why is he rabbiting on about this? Everything in life works like this. The very first browser, the web browser that you're probably using to watch this video, had a limit as to how big you could type in a URL. That's the address that you type in at the top. And the limit was 1024 because somebody said, no one's ever going to have a domain name that's bigger than 1024. And it turned out then we started putting all kinds of other parameters on the command line or on the URL line, and suddenly we needed things that were longer than 1024, and browsers didn't work. And they had to be patched, and everybody had to update to the newest version because it turned out that was an arbitrary limit that was wrong. Probably 50% or more of all security problems that you hear of where there's a vulnerability with this piece of software and everybody needs to update their computer, or you're going to get a virus or you're going to get malware or something else, 50% of those are caused because somebody went through and picked an arbitrary value that made perfect sense to them at the moment that they picked it, and it turned out to be wrong. And now there's an issue in the software where that arbitrary limit can be exploited in some way. So, using arrays when you don't know how big the data is going to be is probably not the right answer. Great. So cool, and that's a really long story, but it turns out we've all known about array lists for a long time and they dynamically grow and shrink. So I don't know why you've been telling us all this because obviously the right answer is that we should just use an array list. Cool. Well, first off, let's look at the word array list and let's look at what's at the beginning of it. There's the word array. Why is that in there? Because underneath an array list, they actually store the data in an array. That's how array lists work. So if I tell you that I need an array list of, let's say, strings, what it actually does is it super secretly behind the scenes makes an array that has 16 cells in it. I'm sure I miscounted that, but we're going to pretend like that's 16. Why 16? Because somebody picked an arbitrary number and it's 16. So, when I say I want an array list of strings, it makes an array with 16 cells in it. If I put more than 16 items into the array, it just automatically grows the array for me. But Enda, you told us arrays cannot grow or shrink. Once they're created, they cannot change size. Correct, they cannot. So how exactly does it grow the array? Well, if I go and try to put in another item in here, so I've filled in 15 items already, we're pretending like this is 15, and I go to put in my 16th item, what happens secretly behind the scenes is that Java creates a bigger array. In this case, it's going to be about 22 cells long, about time and a half, so 0 to 21. It copies all of the data down from the original array. So it puts all of the data back in from the original 15 cells. And then in the 16th cell, which it now has, it has room to put in my new data. And that works up until I put in my 21st thing, and then it adds in time and a half again to make the array bigger. And each time that I go to add a new item in that's bigger than the size of the array, it has to do this operation of making a whole bigger array, copying all the data down, destroying the old array, and then allowing me to do the insert for the next one. And we briefly covered this when we talked about linked lists, but this is kind of a terrible implementation. If I know that I'm going to put 500 students in my array or 500 classes in my array of classes, then 500 was an arbitrary limit if I made it an array. By making it array list, I have the ability to add a 501st or 502nd, and I have solved my problem. But along the way, when I went to put in the 15th item or the 16th item, and when I went to put in the 22nd item, and when I went to put in the next biggest item, it had to do all of this work to copy the array down. And that's real work. Every one of those copies is something that's done in a loop. So, I mean, there's code that's running that says, oh, you want to insert into this array list and it's a little bit too big, or the array list is a little too small and the data is bigger than the size we have. Hold on, let me run a loop that creates a new array that's time and a half the size that we currently have. Let me, with a loop, copy all the data down. Then let me answer your request to add that one more item into the array list. And that's going to happen over and over and over again each time it exceeds the boundary. Now, why does it increase by time and a half? Honestly, it depends on your implementation of Java as to what it does. In most implementations, it takes the array and increases it by half again. It can increase it by up to 2 in some implementations. It's ill defined as to what the original rule was. So it just depends on the implementation. So what I'm telling you is if you use an array list and the person running your code is running the Oracle JDK, it may behave differently than somebody who's using the Microsoft JDK because their implementation of array list might be slightly different. So fun times with all of that. But it works and it definitely grows and it avoids the security problems that we've been talking about, but it's not very efficient for memory. As we mentioned when we first looked at ArrayList, imagine the circumstance that you have an array list that already has a million items in it. And imagine that that's the current size of the array. So this is a really big array, obviously. And so here you are, 0, and down at the end, you're in cell 999999. And you're about to add one more cell in there. Well, now it has to grow the array by time and a half, which means you're going to now be at 1499999. And all that was created just to hold one more item. If the item is a student, it might be that each student occupies a kilobyte of RAM, so 1,000 bytes. That's plausible depending on how big the data is for each student. So you've suddenly allocated another 500,000 kilobytes of RAM just to be able to store one more student. That's very, very inefficient. And that's why array lists, while they are kind of magical and they kind of just do stuff for you, they're not always the right answer. If memory is a concern, array lists are a terrible idea to use because of the fact that they grow by time and a half. Okay, so all of that gets us back to the idea of this linked list. So in a linked list, the advantage is that however long the list is, if I want to add an item in, it simply just adds the item into the list. It just adds one more node, which is the new node that's going in, and then it links it to the end of the existing list instead of using that null at the end. And so the amount of memory that a linked list uses is always the correct amount. However many items I'm storing, that's how many items it's going to store in the linked list. That's how many cells it has in the linked list or nodes it has in the linked list. If I remove one, the list is one shorter. If I add one, the list is one longer. And there's no doubling or time and a halving that happens at any point throughout the implementation. So it's much more efficient from a memory usage. Cool. So why don't we just always use a linked list then? Because it sounds like they're better than arrays. Well, the problem is getting to an arbitrary cell in a linked list is harder. So in an array, if I want to get the data that's in cell number 1, I simply access the array at position 1. And in one operation, it's able to tell me whatever is in here. But if I want to know what's in item 7 of a linked list, the only way it can access the list is through this front link. And so it has to look in here, and then look in here, and then look in here, and then look in here, and keep going until it gets to cell number 7. It has to look at each cell in the linked list one at a time as it's going by to figure out where cell 7 is. And that means pulling an item out of a linked list I can do in one operation. I just say, give it to me, and it gives it to me. But pulling it out of a linked list, did I say that backwards? Pulling it out of an array, it's one operation. Pulling it out of a linked list, it's 7 operations to get the 7th cell. It's a million operations to get the millionth cell. Whereas in an array, it's one operation to get the millionth cell. So what I'm telling you is there is no right answer to which data structure is the best, because the answer is determined by what your primary concern is. If your primary concern is memory usage, then arrays and array lists are probably not the right answer, depending on what you're doing. If you're concerned about memory, then linked lists are probably the right way to go. But if you're concerned about being able to get data out of the array list, array, or linked list the fastest, then using a linked list is probably not a good idea, and using an array is the right idea. And what you're going to notice is that up until now in 1321 and 1322, we've always given you absolutes. If you need to do this, you do this. But now I'm going to start telling you that's not how the real world works. All of these data structures that we're going to talk about in this slide deck all exists for a reason, because they are better at one thing, but there's a cost to that in some other direction. And so you're going to have to, as a software developer, this is honestly what you're being paid for, is to figure out which one is the better one to use given the parameters that you're working with. Is it more important that you be able to get data in and out? Is it more important that you use less memory? One of those is probably true, and it depends on the application that you're working for. Sometimes putting data in is more important than getting data out. Sometimes getting data out is more important than putting data in. Take KSU. How often do we add new students? Well, we really only do that once a semester, right at the beginning of the semester. But how often do we have to look at the existing students that are in the list? Well, that happens thousands of times a day. I have to look stuff up all the time. And I have to go and ask for, give me this student so that I can see what class they're enrolled in or see what grade they made. So there's thousands of people asking to see data, and that ability to query the data is way more important than the ability to put new data in. If it takes a minute to put new data in, yeah, it's slightly annoying, but it doesn't matter. You can do that overnight on the beginning of the semester while the processor is running and we're all asleep in bed. So the reality of what you're doing with the data determines which one is better. So as a software developer, what you need to understand is not that there is one data structure that is the right one that you should always use, but instead you should realize what are the pros and cons of each data structure that we've shown you, and be aware that they all exist, so that when you open your toolbox, you have the appropriate tool for the job that you're at hand with. Okay, so let's talk about the implementation of linked lists. Again, if we ask you to use a linked list in a test, we're asking you to use the built-in linked list that Java has. You don't have to implement it from scratch, although we are going to show you how to implement it from scratch so that you understand what's going on underneath the covers, because it's important to understand it so that you know when it's appropriate to use it. So that is what we are going to do. So we're going to build a linked list class. If you're going to build a linked list class, you need to know what type of data you're going to store in there. We're not going to build a generic one. We're going to build one that is specific to one particular type of memory. So in order to do this, or one specific type of data, in order to do this, we're going to create a new class. Now, this is going to be something that's going to be a little weird. And as we're going through this, you're going to think, huh? Does this work like this? Okay, so the first thing is we're going to create a new class called node. You can call this whatever you want. Node is just a convention. It tends to be what people call the node in a linked list because that's convention. So inside of the node, you put all of the data that you want to be able to store in each node. So, for example, this is effectively the type of data that you're going to have in your linked list. If it's a linked list of students, in here you'd have the KSU ID and the name and the address and the phone number and the GPA and the list of classes. All of that would be data that you would put into the class node. And then the second thing, and this is the part that's going to be a bit confusing, you're going to put in a reference or a link to another node. Okay, so let me pause there for a moment and point out we are creating the class node, and inside of the class node, we are referencing a data type called node, which is actually the class that we are currently creating. And we're going to call that next. You can call it whatever you want. Next is not a magical word, it just happens to make it make sense. So by convention, you typically call this next. So a node class will have however many attributes you want to store data for, which in this example is one, and we're just calling it data, but certainly there could be 10 or 15 or 100. And it's going to have a next link that connects you to the next node in the linked list. All right. So each of these nodes that we just created look like this item down here that has the 15. The data is where we're storing the information that we actually want in the node. And then this is our next link that connects to the next node in the list. And each one of these nodes is linked to the next node, hence the name linked list. So a linked list can be thought of as a chain of linked nodes, which is exactly what it is. The node has at least two attributes, data and the location of the next node in the chain. If you're going to have nothing at the end of the chain, wherever your chain ends, you're going to point that last node to some magical place called null. This is just to indicate that that is the end of the chain. I'll explain that in a bit more detail as we go on, but the short version is null is just a magical place in the computer. It's usually memory address 0, but it could be somewhere else, that is simply used to indicate there is nothing here. It's an absence of a value. When you create an array list or an array, before you do the equals new, the array list is actually pointed to null because it's not actually there. And then the moment you do new, it creates the memory and actually updates the link to point to there. Not setting that last node to null or the last link to null is considered an error because there's no way to know that you've reached the end of the list since each arrow just points you to another place. You could conceivably keep going even though there's not really meant to be anything down there. So it's very important that you always update the end of the list to be null. Okay, so things you might want to be able to do with a linked list. You might want to be able to insert a new node at the beginning. You might want to be able to insert a node at the end or put a node somewhere in the middle. You might be able to delete a node out of there. You might be able to search. You might be able to sort. And each of these are going to take some amount of time to implement with a linked list. So we're going to take a look at some of those ideas. So the first idea is inserting at the front. So this is our existing linked list. We have a head here, which is just how we access the list. Again, head is not a magical word. You can call it start, front, head, whatever you want. Convention says it's called head. And it just is a link that connects us to the beginning of the linked list. That really only connects you to the first node. And then in turn, the first node links to the second node, which links to the third node, which links to the fourth node, which links to null, which tells us that's the end of the list. And that's how all linked lists work. Okay, so in this case, this appears to be a linked list that's storing integers. The first node has a 7, and then a 5, and then an 8, and then a 2. All right, so to make a new node that we're going to insert at the front of the list, the first step is we create a new node. Now that node is just a class, it's called node, and I literally just instantiate it like I instantiate a new student or a new employee. I say node, my node equals new node. Into that node, I'm going to fill in the data that I care about. So node.student name is equal to M. Sullivan, node.ksuid is equal to 12345, and node.address is equal to 123 Main Street, whatever. So I'm going to fill all the data in there to populate the node. The next link that's in the node, remember that every node, if we go back to the definition, has the data, which can be more than one attribute, and then it has this next thing. The next link that's in the node, you're going to start off with it pointed to null. That's automatically done by Java. Anytime you create something, Java automatically sets it to null for you. So it's pointed at null, head is still pointed at the original list. Nothing has changed in the original list yet. We just created a new node, which right now is not linked to the linked list. Okay, so the next step is we take this arrow, this link called next, and we set it to the same place as head. That has the effect of it linking to this node and head also linking to this node. There can be more than one thing linking to the same place. All right, so we're still not in the linked list, but now at least if you were to somehow come into the new node and ask it to go to next, you'd get to the beginning of the list, and then next, and then next, and then next, and then null. So now the last step is we just need to move the head link up to the beginning of the list, the new beginning of the list, which is to that new node. So we point head to the new node. And that means head is now pointed at the node that has a 6 in it, which is the beginning of the list, and it points to the node that has a 7, and so on and so forth. This successfully inserted this new node with a 6 in it at the beginning of the linked list. That is what we were trying to do here. Okay, so the steps were you create a new node, you point the new node's next link to the same place as the original head of the list, and then you change the head of the list to point to the new node. So it's actually really just 3 operations to get it in there. All right, how about deleting an item out of a list? Well, if you're deleting the item that's at the front of the list, it's actually quite easy. So assuming that we have our head here at the beginning of the list, all we need to do is move head from here to here. Once head is pointed at this second node, then all of a sudden we have effectively removed the first node because there's no way to get to it. If you notice in a linked list, the only way to get to any node is to start off with head and then move to next, next, next as many times as you need to until you get to the node that you are looking for. So effectively, by moving head, you can erase nodes. Now, does it actually erase the node the moment you move the head? No. But what happens is the garbage collector, remember that fun thing? It realizes nobody's linking to that node anymore, and so it deletes it. You might say, well, how does it know that no one's linking to it? It keeps track of everybody that links to any spot in memory. And if that number ever reaches 0, it assumes that that block of memory is no longer in use. It garbage collects it, returns it back to the empty pile. So all you have to actually do is move head from head to head.next. Okay, so let's talk through head.next. If this is head, it's just a link that links to this first node. And inside of here, we might have data. This might be the 7 would be data. If I were to print out head.data, I would get the number 7. If I were to ask for head.next.data, I would get the number 5. And that's because I'm saying take head, follow it to the next link, then look for the data attribute, and that gives me the 5. Remember that each node has 2 attributes in this example. It has a data and it has a next. The next is the arrow, the data is the number or whatever it is that you're storing in the linked list. So printing head.data would give me 7. Printing head.next.data would give me 5. Printing head.next.next.data would give me 8. Head.next.next.next.data would give me 2. And if I were to ask for head.next.next.next.next.data, I would get an error. The exception that will be thrown will be a null reference exception, and the program will crash. You're not allowed to go past this point and ask for anything out here because this is defined as the end of the list. So never look into null. Null is this place you're never supposed to look. All right. So deleting a node out of the list was simply setting head to be equal to head.next. Just like if you take a number, let's assume you have an x attribute or an x variable, and you set x equals x plus 1, it adds 1 to x, which gives you whatever the new number is, and then it assigns that value to x. X equals x plus 1 gives you the new value of x. Likewise, head equals head.next makes it such that head is now pointed to where head.next was pointed, which is the second node in the list. So deleting an item from the beginning of the list is nothing more than setting head to head.next. Deleting an item that is not the head of the list, so an item in the middle or an item at the end of the list, is a little bit more tricky, but it's not impossible. Usually, what you're going to do is you're going to have a head, which you don't ever mess with head, because as you saw in the previous example, if you change head, you've lost data. So you don't change head usually. What you're going to do is you're going to create a current or a previous or whatever you want to call it link, and you're going to point it to the same place as head. Then you're going to move current down the list until you get to the node before the node that you want to delete. So in this example, we're trying to delete this 8 node here. So what we're going to do is we're going to move current or previous or whatever we're calling it until it's linked to this node. Once we're here, we're one node away from the node that we want to delete. But this node's next, which is the one that used to link to the node that we're trying to delete, is what needs to be updated to this node's next.next, which will get you over to the link past it. And once this happens, there's nothing referencing this node and it just goes away. So the delete method is find um, find where you're trying to delete the node. There are three possibilities. One is the node that you're trying to get rid of is at the head of the list. That's where we just move head. Another possibility is that it's not at the head of the list, and that's where we're going to need a current or a temp to work our way down the list and find the node before the one we're trying to delete. And then finally, the other option is you're asked to delete something that's not in the list. Well, if it's not in the list, you successfully deleted it because it's not in the list. So here's a list of 3 students, and Enda is one of them. You tell me to delete Enda. Okay, I update my links, and now Enda's gone. You tell me to delete Enda. Done. Tell me to delete Enda. Done. Because it's not in the list. I don't have to do anything. All right. So you would have to iterate through the list to find the node that you're wanting to get rid of, and that's done with a loop that looks through it. So we're going to take a look at some of the code. All right. So we're going to start off here and we're going to build a linked list of integers. Again, let me preface this by saying this already exists in Java. You don't actually have to build this every time you want to use a linked list. You simply instantiate a linked list. But again, we want you to understand how it works so that you have an understanding of why you might use it. So building a linked list class, I would say public class linked list class. Don't call it linked list because again, there's one already there. So the first thing that I have to do is I have to declare that node class. Now, this is a weird syntax that you've probably never seen before. Inside of a class, it's actually possible to declare another class. What? Okay, so if you do that, the inner class, the one that I have highlighted in that orangey brownie color, whatever that is, gold. Let's call it gold. The color or the font, the text that's in gold there, is only available inside of the linked list class. It's a class that only exists inside another class. In actuality, what I'm usually doing when I do something like that is I'm declaring a static class that's actually only in existence inside of its parent. You don't have to do it this way. You can absolutely create the class separately inside of IntelliJ. And that's what I'm going to do when I do the code inside of IntelliJ instead of actually putting it in the class. So let's hop out to an IntelliJ window here and let's actually do this. So I'm going to say file new Java class and I'm going to call it node. And let's make a linked list of strings. So just so it's slightly different to what we have in the example, because that's a linked list of integers. All right, so what I'm going to do is I'm going to store a linked list of names. So I'm going to say string name, and then I'm going to have this weird part, which is the next. So I'm going to say node next. Now, in both of these cases, I probably should make them private, but it's actually easier if I make them public for the sake of this example. So for the sake of this example, I'm going to make them public, but please note, this is not good practice. They really should both be private, and you would have to deal with the details of the public private stuff throughout your code, where you'd have to have getters and setters instead of just directly accessing them. I'm going to do it with public just for clarity so that you understand what's going on. All right, so now I'm going to make my linked list class. So new Java class, linked list class. All right, so in my linked list class, I'm going to need a constructor. So that's public linked list class, has no parameters. And I'm going to need my head, which is the beginning of the list. So I'm going to say node head. All right, so that makes a link That link currently is pointed to null because, as I said, until you instantiate it, there's nothing on it, so it always automatically updates it to null. But just to be absolutely sure of that, this is redundant. I'm going to set head equal to null in the constructor. This automatically happened, but I just want to do it so that it's very clear that we're starting off with null. All right, so we're going to add a method for adding things to my linked list. I'll call it add. All right, so in order to add, I need to take in a string because I'm presumably adding a string to my linked list. So new data. Okay, so what I'm going to do is I'm going to go back and look at my node class and remember what I called it. I called it name as the string. What I'm going to do is I'm going to say in my add, I'm going to make a new node. So I'm going to say temp, which is of type node. So node temp equals new node. That's just creating a new instance of this node class that I just declared over here a moment ago. And then I'm going to say temp dot name is equal to the new data. So whatever data they passed to me in this parameter, I'm going to stuff that into temp.name, which is the name attribute inside of this node. All right, so far I've made the node. I haven't actually done anything with it. I've just created it and I've put the name into it. So there's a couple of possibilities of how things look. And my computer has gone to sleep. So let me wake up my computer. All right, here we go. You're offline, reconnecting. Yay, there we go. Okay, so one possibility is, and if we just erase this, there is currently nothing in the linked list. And that's very plausible. We certainly could have a linked list with nothing in it yet. Um, Let me flip that over so that I can actually see what I'm doing. All right. So right now, head could look like this. And that is actually what we are thinking head looks like, because right now we're thinking that head is empty. I guess I should erase this stuff down here for clarity as well. So let me get rid of that guy. Okay, there we go. Um, all right. So in this scenario, what I'm doing here is I've made a new thing called temp, and I've asked temp to get a new node. That new node comes with its own link, and that link right now is linked to null, and that's how you draw just two lines like that. And then into temp, I put the name. So here's enda, right? I put it into the data field of that node. That's what I've done so far in my code. Okay, so now what I need to do is I need to connect this to the list. If I know that the head is the only thing in the list and it's currently pointed to null, then I could simply just set head equal to temp. And that would have the effect of connecting head to the beginning of the list. So if there's nothing in the list, then that's how I'm going to do it. So let's go back to my code and let's say that. If the head is currently null, then all I need to do is say head is now equal to temp, right? And in the picture, that is this arrow. Oops, that is not turned on. This arrow now links to there, and the original thing that was the null is gone because that's no longer where I'm pointing. So this is how the picture looks currently. And you might say, well, there's this weird temp thing, but realize that in my code, temp is a local attribute. It only exists inside of this method. So as soon as this method is over, temp is going to go away. And when temp goes away, notice what I'm left with. I'm left with a linked list that has one node in it, which is exactly what I wanted. Okay, let's assume that somebody calls insert again. So when they call insert a second time, we're going to make a new temp. It's going to link to another node, which is going to have a null at the end, and we're going to put in the new name. This one is Paul. Okay, so now how do I link this one to there? If I update head, which might be your initial reaction, watch what happens. So I move head down to here, and then this goes away. What's going to happen? Well, what's going to happen is the garbage collector is going to come along and it's going to realize that this is no longer being linked to, and it's going to garbage collect it. And I haven't so much inserted Paul into the list, I've replaced the list with Paul, which is not desirable. That's not what I wanted to happen. So, in order for that to not happen, let's put my node back. I can't change head directly. Instead, what I want to do is I want to update this link at the back. Let's change this color. This link right here, I'm going to update it to link to the front of the list. Now I can change head because there's now two ways to get to enda. Enda is both from head.data, or head.name in this case, but it's also known as temp.next.data because of this next arrow out here, temp.next.data. So once I've updated this arrow, then I'm free to move head. And so now head can point down here safely. And when everything erases and all the extra bits go away, I'm left with head that links to Paul, that links to enda, and I've successfully inserted at the front of the list. Okay, so let's take a look at how that looks in code. So this is not the scenario that head is null. This is an else. And in my else, what I'm going to say is temp.next is equal to head. That is the green arrow in this picture. If I put temp back in there, because I haven't gotten rid of it yet, temp was here, and I said temp.next, which again, I can change color here real quick, is this arrow. That is temp.next. I've pointed it to the same place that head is pointed to, and before I updated the picture, head was pointed to here. So temp.next points to the same place as head. That gets this arrow updated. Then I'm going to say, now you can move the head to temp, which is what I did up here, but I have to do this step first. The order in which I do these steps is very, very important. So now that this link has been established, the blue link, I'm now free to update head. And instead of head pointing to enda, it now points to here. And again, when the method ends, temp goes away because it was local. So that disappears. And I'm left with head linking to Paul, which links to enda, which links to null. I have a linked list. And yes, it's a bit wiggly, like I did it in weird, squiggly lines. But if you draw it out in a straight line, it's head linked to Paul, which links to enda. This is the same exact thing. I'm just drawing it in a straight line to make it clearer. All right. So I've successfully inserted at the front of my list. All right. So let's take a look at how we would remove something from the list. So we're going to do public, and in this case, it's probably going to return a string because it would be nice if I got back whatever was in the list, or maybe I don't. Let's do void. Remove, and I probably need to tell it which node I want to remove. So we'll assume that we're going to tell you by a number. So I'm going to say int position. You could certainly have it so that it takes in the value and it looks through the list to find that value. You could do all kinds of things like that. All right. So again, let's go back to our picture and let's talk about what's going on here. So we're presuming, ooh, that is not an eraser. That is still not an eraser. There we go. We're presuming that we already have a linked list in this scenario. So let's give ourselves a nice clean list that is easy to read. Okay, so we have head, and we have a link, we have enda, we have a link, we have Paul, we have null. Okay, so we're presuming that's what our linked list looks like. What we're going to be able to do here is we're going to be able to say remove 0, and that's going to get rid of this node here. That's what we're trying to do. Or if I told it to remove 1, then it would get rid of this node here, because that's node number 1 in the list. So that's what we're trying to do. All right, in order to get rid of this first node, effectively what I'm going to need to do is I'm going to need to change that link to link like that. Once I change this link and I get rid of the original, Enda is no longer linked to, and it's going to disappear. Only Paul is in the list. So that's how we remove if we're at the beginning of the list. All right. If it's anywhere later in the list, then we're going to see how to do that. So let's work on deleting at the front of the list first. So if you tell me to remove 0, then all I actually have to do is say head equals head.next. Okay, let's look at this. Head.next, in this original picture before I drew in the extra blue arrow, head.next refers to this link. That is head. That is head.data. That is head.next. So head.next refers to that link right there. And so what I changed was I changed head to be equal to head.next. So head is no longer this, it's now that. And that has the effect of the garbage collector will come along and will remove my enda node for me. All right, so I'm going to put it back and we're going to take a look at this in code again. So if position is 0, meaning you're asking me to remove the first element, all I have to do is set head to head.next. Now, in the picture that we're looking at, that is completely valid code. What happens if this is the current state of the list? Well, head is equal to head.next, which is what? There is no head.next. This is null. So this will actually cause your code to crash. Because if the list is currently empty, head.next is not defined. So I need to check and make sure that head is not empty. So if head is not null, then I'm welcome to do head equals head.next. If head is null and you're asking me to delete position 0, ding, we're done. There's nothing to do because there's nothing in the list. There never was. So it just depends on whether there's something in the list or not. All right, so that's deleting position 0. In all other positions, so if you ask me to delete position 1, position 2, or position 3, let's take a look at how this is going to work. So again, we're going to need a temporary thing that links to the list. So generally what we're going to do is I'm going to call this current. You can call it whatever you want. I'm going to call it current, and it's going to start off linked to the same place as head. I'm going to add a third node in here just for the example, because it'll make it a little bit easier to understand rather than trying to do this with just 2 nodes. So back to whatever pink color that is, and we'll put Jane in here. That's a Jane. All right, and Jane has a null that's linked off the edge. There we go. Okay, so we start off with current, and what current is linked to right now is the node that has enda in it. And then we're going to keep moving current down the list until we get to the node before the one we want to erase. So let's imagine we've been asked to remove 1. What that refers to is the node that has Paul in it, because effectively that's 0, that's 1, and that's 2. So we're being asked to remove Paul, is what remove 1 would ask us to do. So what we would do is we would move current down the list until current is at the node before the one we want to erase, which in this case is enda. So it actually doesn't have to move anywhere. Once we're there, we tell it to update the node that I'm going to highlight in blues, or the arrow that I'm going to highlight in blue here. We want to update that arrow to look like this. And that's what's going to erase Paul. So there's 2 steps. Step 1 is moving current down the list until we get to the node before the one we want to erase, which in this case was done because it was the first node. And then step 2 is updating it. So let's go back to our code and see what that looks like. So what I'm going to say is while, so we're going to say we have to create our current first. So node current is equal to head. Right now it starts off at the beginning. And I'm going to create a temp position, which is going to tell me where I am in the list. So temp position is equal to 0 because the head is position 0. So while the temp position is less than position minus 1, because I want to stop one node before where I'm being asked to erase, we're going to set current equals current.next. Okay, so what those lines of code are going to do is they're going to say, take the current, the current link, which is this guy over here, and while we are less than the number they're asking me to remove, keep moving it down the list, pointing it to each node one at a time. So just as an example, let's assume that we're asked to remove 2. So instead of that being a 1, we're going to presume that is a 2. Okay, so in this case, current starts off pointed to head. Our temp position, which I'll keep track of here, is equal to 0. All right, so what my loop says is, while the temp position is less than this number minus 1, which this number minus 1 is 1, so while 0 is less than 1, move current, which is this, to current.next, which is this. So current is going to move to here. Now, temp position gets updated to 1, and it checks, is 1 less than 1? It's not. So now I have stopped one node before the one that I'm trying to erase, which is this node. Okay, so the only thing I forgot to do in my code, by the way, is I forgot to update temp position to plus plus, because each time I go, I need to update the temp position because I've moved 1. All right, so this block of code has the effect of moving my current to the link before the one I want to erase. Once I'm there, I just have to make sure that there isn't a null there. So I say if current.next is not null, then I'm going to set current.next equals current.next.next. Oof. Okay, so assuming that we're back to the scenario where we're erasing node 1, what's going to happen is my current is going to be here at the end of the loop, and the temp position is irrelevant at this point. All right, so I'm being asked to erase the cell at position 1, which is the cell that has Paul. So what I said is, I want you to take current, which is this link, and look for its next, which is this link. So current.next, and set it equal to current.next.next. So current.next, which I'm going to make yellow, gets set to current.next.next, which is blue. So effectively what's going to happen is that is going to get linked to there. And when I link that to there, the existing node, or the existing link, is gone. So what's happened? At this point, it's irrelevant what's going on with current, but you can see if you trace head links to this node links to this node, and we've successfully removed Paul from the list. All right, so that's all if current.next is not null, because if current.next was null, there's nothing down here and I can't keep going. But again, in that scenario, I can't delete it, so yay, we're done. All right, so that is the code for removing and linked an item out of a linked list. Again, I'll state the same thing I've said 3 times now. You're not expected to write this yourself, but we do want you to understand how it works. In the end, everything in a programming language was written in code. Somebody sat down and wrote this, and you can now just use it. You're just getting to use code that somebody else already wrote and debugged for you. But it's still good to understand how that code works so you understand at a high level how a linked list actually works. Okay, so that is our linked list of ints, and that has the add node, and it also has an add to the back of the list. And I've shown you how a remove works. This is doing pretty much the same thing as I did in my slide, but it's naming things slightly differently. So you get a different example. This is a display method, which just prints out everything in the linked list. And again, you're going to notice here that we tend to have a lot of these loops, current equals current.next. That's how you move through a list. You don't want to be changing head, because if you change head every time you print the list, it's going to delete the entire list. Generally, unless you are updating something where you're removing the first item out of the list, you're never going to change head. You're going to make a current or a temp or whatever you want to call it, set it equal to head, and then use the current to move along the list so that the original head is never messed with. And then all we're doing here is just printing out the data or returning the data that's in each of the nodes. Okay, so write a method that would sum up all the numbers held within a linked list and return the sum. So presuming that we have a linked list with a bunch of numbers, how would you go about summing them up such that you got the sum of all the numbers in the linked list? So I'm gonna erase my old list and we're gonna make a new list, and this time we're gonna put numbers in it. The only thing that changed here is that it would have numbers instead of strings. So we'll do head. Let's not use this yellow color. Let's go back to red. Okay, so we have head. Also, why is that so incredibly thick? Let's erase that. Oh my gosh, that's so much better. All right, so head has the first node, which has a 1 in it, which has another node, which has a 2 in it, and another node, which has a 3 in it, and another node, which has a 4 in it, and then we have our null. And our goal here is to sum up all the numbers in the list. So graphically, what we're going to do is I'm going to make a temp. That temp is going to be linked to the same place as head when I start. I'm going to have a sum variable because I need to keep track of the sum, because that's the whole point of this. And what I'm going to do is I'm going to say add to the sum whatever is in temp dot data. Then I'm going to move temp to temp dot next, and I'm going to add to the sum whatever is in temp dot data. And then I'm going to move temp to temp dot next and add to the sum whatever is in temp dot data. And again, temp to temp dot next, add to the sum whatever's in data. And one more time, I'm going to move temp to temp dot next. And at this point, I'm going to realize I've hit null. And so I'm going to stop and return whatever I had in my sum. So that's what I'm doing graphically. Let's do that with actual code. So this doesn't really work for my array because my array here is of strings, but I'm going to write the code as if it works. So public int sum. All right. So we're going to make a temp. So node temp equals head. That just makes the initial temp that's starting off linked to wherever head is linked right now, which is here. Okay, once I have that, I'm going to have a loop that's going to say while temp is not null, I need to say sum, which by the way, I should probably define as an int that is currently 0, plus equals temp dot data. Okay, now it's screaming at me because I don't actually have a temp dot data in my node class. I currently have a temp dot name, but no data. So let me go ahead and add a public int data. So that's perfectly valid. And then back in my class, I simply say while temp is not null, sum equals temp.data and temp equals temp.next. That's what moves temp on to the next link in the list. So we start off here, we add temp.data, which is this one. Then we set temp equal temp.next, which moves temp down to there. And now we do temp, or sum equals sum plus temp.data. All right, and so that's going to give me all of my data. At the very end of this, I need to return the sum. That's all there is to it. That's actually pretty easy. All right, so let's take a look at our slides, and we're going to see that there's actually two solutions to this. So the second one is the one that I just did. It's the iterative solution. It's using a loop. So basically, it set the sum equal to zero. It presumes there's a current here, and it says, well, that current is not null. Add to the sum whatever's in current.data and set current equal current.next. Finally, return the sum. Great. That's my iterative solution. There's another way you can do this, and I know the last thing you want to hear right now is recursion, but you can do this with recursion as well. So double sum node current. If current is null, return zero. So if you're given a list where there's nothing in the list, then the answer is zero. Otherwise, return current's data plus the sum of current next. This requires you to pass in the link as the parameter, but basically this is your recursive call, and in your recursive call, you're passing it current's next so that the next time the node starts off, it's one further down the list. And all it's doing is it's adding the data in there to the sum of the rest of the list. This reads like English. If current is null, so if the list is empty, return zero. Otherwise, return the current data plus the sum of the rest of the list. All right, so you can absolutely do things recursively or iteratively. These will both get you the same answer. Write a recursive method that adds 10 to the data in each node of a linked list. Okay, so we're just going to take a look at the answer to this. Void add 10, it takes in again a link. And if the link is not null, it adds 10 to the data in there and then calls itself again with n.next. You'll notice this is a very elegant solution, as is the recursive solution that we saw for summing the numbers. Quite often with data structures, you're going to see recursion. If you are a CS major or you're a software engineering major, the next class you're probably going to take is a data structure class, and you're going to spend an entire semester looking at these things and you're going to be doing them all recursively. So if you thought that your nightmare of recursion ended 2 weeks ago, I have very bad news for you. It's not going away. It's going to keep coming back. As a matter of fact, when we get to graphs and a couple of ones, it's really the only way you can do it. So recursion's here to stay. But anyway, that brings us to the last topic in linked lists. Unfortunately, with linked lists, it's quite difficult to access nodes that are in the middle of the list or nodes that are near the end of the list. So let me clear all this up and redraw my list so that it's a nice clean list again. And so we have our head, and it has a list with, a couple of nodes in it, and life is good. Remember that, like in these examples, I'm drawing it so that you have 3 nodes, but of course the linked list could have a million nodes or a billion nodes or 100 billion nodes. And so if I ask you for the last item in the list, right now you have to start at head and work your way down the list a billion times until you get to the node that I ask for, which is not very efficient. So people wondered, is there ways to make this faster? Because it turns out accessing things at the end of the list is actually a pretty common request. So the answer to that is, why only keep track of the front of the list when for double the complexity, you can keep track of both the front and the back of the list? So what I'm suggesting is, in addition to the head, you could also keep track of something else. We'll call it tail, which keeps track of the tail. And this will always link to the last node in the list. This allows you to get to the end node very, very quickly. So how do you make this work? Well, there's no magic to it. And again, I want you to be very clear that the words head, the word next, and the word tail are not magic. They're just words that mean what they mean because of the way that I build a list. And likewise with tail, all that happens is when I make the list, so in the beginning, you've got head and tail, and they're both linked to null because that's what the list looks like when there's nothing here. When I add the first node to this list, it's going to look like this. Head and tail are still pointed to the same node. But if I then add another node to my list, what's going to happen is the new node is going to get created. So here's my new node. We'll call it temp. I put the number 2 in there, and then I set its next to head. And then I changed head to the new node. When everything cleans up at the end of all of that, what I'm left with is head links to this node, the second node effectively. It then in turn links to this other node, and that links to null. So I've successfully inserted at the front of the list, but by not messing with tail, tail is now pointed to the last node in the list. And if I repeat this process over and over again, where I keep adding more items into the list, then effectively what's going to happen is the tail just kind of keeps moving along with the list and it stays at the end. Now, this all presumes that I'm adding my new items to the head of the list or the front of the list. It is also possible to add items to the end of the list. And if I do that, then I do have to update tail each time I do it. But again, I simply made another link. All I did in my code was I just added a tail and I set it equal to the same place. And in the beginning, when I add nodes into the list, I just moved tail to also equal temp on that first move. And for here on out, I don't ever have to mess with tail. Now I have a head and a tail pointer. Well, that makes it easier for me to find the end of the list. But what happens if I need to find something that's the second to the last node in the list? Well, then again, this really doesn't work very well. I kind of just have to start with head and work my way all the way down the list. And the tail really didn't buy me anything, which is where you get the idea of a doubly linked list. So, a doubly linked list is nothing more than a linked list where you happen to keep track of two links in each node. So, in addition to the next, which you've always been looking at, we also put in a previous. And in this case, the previous on the first node would point to null because there's nothing before the first node. The previous on the second node points to the first node, and the previous on the third node points to the last node, or to the second last node. And again, the next points to null at the end. So you might say, well, how do you make the arrows point in a particular direction? You don't. The only reason that they're being drawn in this direction is because that logically makes sense to me, but that's just me. In the computer, they're not in a straight line, they're wherever they happen to have memory. And so this is just a visual representation of a linked list to our brain, something that makes sense to us. But in reality, what's happening in the computer is they're just all individual links to blocks of memory somewhere, and they're all over the place. It's not in a straight line. As you saw when I added new nodes in, they tended to all look like they weren't in a straight line. They were all wiggly and whatnot, and that's more close to the reality. But when you picture it, you're going to picture it this way. Okay, so how do I add a new node into this linked list? Let's assume that I want to add a new node in here, in between 1 and 2. So I'm going to do the same things as before. I'm going to say temp is equal to a new node. I'm going to put the value into it. So temp.data is equal to 4. And then remember that I have a next. I'll designate that as an n. And I have a previous. And Java will nicely initialize both of those to null for you. All right, so to insert it in where that arrow is, I've just got to do a bit of basket weaving. And it's important that I do the basket weaving in a particular order so that I don't ever lose anything in the list. So what I'm going to do is I'm going to take this temp.next, which is this one, and I'm going to link it to head.next, which means it now links there. And it's no longer linked to null. All right, then I'm going to take temp.previous, which is this link, and I'm going to set it equal to head, which links it to there. All right, now I just got to update some other pointers. I'm going to say heads next, which is this pointer or this link. Heads next is going to equal to temp. And finally, heads next previous. Let's go through that again. Head next previous, which is this guy, is going to be equal to temp. Oh, that's not red. Make it red. There we go. Okay, and so if we look at everything now, all of my basket weaving is complete. I have successfully linked it such that all of the arrows point to where they're supposed to point to, and my new node has been correctly inserted. It's a lot of updating, so it's more than one. And you might be wondering, wait a minute, what makes it point to one side of the node or the other? Like you're pointing to, what? You're taking this link right here. Let me highlight it in blue, and you're somehow pointing that to this side of the node, but over here you're pointing it to this side of the node. How does it know which side of the node to point it to? It doesn't. There is no sides to the node. It's a random piece of memory somewhere, and these are all just addresses of memory. Logically, up here, you want it to point to the right side of the node, so it makes some sense to you, but the computer doesn't care. The computer doesn't know the left side of the node from the right side of the node. It just knows it as a block of memory. So in the computer, it's not pointed to that side of the node, but logically, we would like to think that it is because it makes more sense to us that way. So all you did was you just updated a bunch of links here in order to make that work. And it's not difficult to do, it's just that you have to keep track of all of those links. And this is just showing you the same information. You can see each of the connections that I did here. And the order that you do them in is important so that you don't ever disconnect or lose part of the list. All right. If you delete from a doubly linked list, it's the same thing. You just got to update a whole bunch of different links. So you eventually isolate the node that you're trying to delete. And that's what happened here because this one points that way and that one points this way. And now nobody's pointed here. So therefore, this node just gets garbage collected and ceases to exist. So, in summary, if you are going to use a linked list, you're going to use the built-in linked list class. It's right there in Java, and all you have to do is say linked list, angle bracket, the type you want, my linked list equals new linked list, angle bracket, the type you want, open close parenthesis, semicolon. Just like you made an array list, except you do linked list. You also have to import Java util linked list. Once you have it, you have an add and you have a remove, and you can do all the things that you would normally do with an array list, but you can know that it's doing it in a more memory efficient way. You can also know that when you ask for node 1.2 billion in a linked list, it's going to take the computer a moment to fetch that data. Whereas when you ask for cell 1.2 billion in an array, you'll get it instantly. And that's the payback that you have of the memory efficiency of the linked list versus the speed of access for the array. So both of these are now tools in your toolbox. Feel free to pull the appropriate tool out when you come across a job. And remember, just because everything looks like a nail, it doesn't mean that you should always use a hammer. Occasionally, you should use a screwdriver for a screw, not a hammer for a screw. So if you feel like you're using the wrong tool, you need to start thinking about what am I gaining by using this tool versus what am I losing? And you need to start thinking in ways like that to make the right decision. Okay, so that completes section 1 or part 1 of module 8. I will see you guys in part 2 soon. Bye bye.